Our final speaker for the day and for the conference is Tom DeSutter. Tom received his PhD in 2004 from Kansas State University, completed his postdoc with USDA in Ames, Iowa, and was hired by the Department of Soil Science at NDSU in Fargo. His primary research interests are saline and sodic soils, reclamation of energy extraction impacted soils, and the instrumentation for measuring soil and physical and biological parameters. Tom teaches introductory soil science, soil land use, environmental field instrumentation and sampling, and is the current editor of Agriculture and Environmental Letters. Welcome here, Tom. Thank you.
So I was a little bit concerned when the hot band comment came up. I thought, if somebody says Justin Bieber, I am out of here. So fortunately, here we are. We got another 45 minutes, 40 minutes now. Okay, so my name is Tom DeSutter. I've been fortunate to come to the Manitoba Soil Science meetings annually for about the last 16 years or so. And those of you that will join us in February, we'll see you then. It has been get off topic quickly, but the coldest temperature I ever was in Winnipeg. It was -40. That was not the wind chill. That was out of the car sort of thing. So thank you for that. So one of the things that living in a semi-arid or subhumid regions, you tend to have a little bit more soluble salts in your systems. And so, oh, okay. And now I got 39 minutes. So it's anyway, so one of the things is, you try to peruse the literature and you find out that, you learn about the distribution of salts in the world. Australia tends to have a lot of saline soils. And so with a population of 8 million people, they have a lot of saline soils for their population. But there was a grassroots effort a long time ago. They created this magazine called Salt. And it was basically how normal people battle salinity. And I have all the copies. Actually, I have e-copies of all of them. I had a student that worked in CSIRO, and he found them at one of the libraries. He didn't steal them; he copied them. But anyway, if you want them, but the quote is really good because it's a difficult problem to sort of manage. And so this guy is like, if you've got salt, learn to live with it. And so part of the, understanding saline versus solanet soils, saline soils just tend to have elevated concentrations of these ions. And so we say salt, but we're really talking about an anion and a cation, right? And so when they combine, they make a crystal. But when they're in water, they dissolve. And then there are anions and cations. So it's not the salt so much that's the problem. It's the concentration of the ions that are in the solution. And so there's terms that are used like, oh, the EC is 4, so it's saline. Well, if your crops aren't growing, you have a saline soil, right? And so it ends up being more about your management than more so a book value. And so our soil survey, soil taxonomy, they use these levels, these defined levels to define taxonomy. We shouldn't be using those as management tools. You should get a soil sample to then figure out what your salinity level is. And so then sodic soils or solanets, these are basically just the excess concentration of sodium with a low electrical conductivity, meaning that they have a low total salt concentration, but the sodium concentration in the soil is quite high. And this is what causes the swelling and dispersion. Not unlike after your Thanksgiving meal, you got your stretchy pants on, you're like, ooh, that's swelling. That's different. Swelling can go in and out. Once you get dispersed, it's over. Okay, so that's what we tend to find is like if you have soils with a lot of smectite clay, montmorillonite, 2-to-1 shrinks well, you will get a lot of dispersion. If you have illite or kaolinite, you likely won't see any at all. It's just that it's not the right properties of that clay. So from a visual standpoint, saline soils are easy to see. You see it on the surface. It can be on the surface, but it all can be what we can call ghost salinity, where it's actually subsurface, high concentration. It just doesn't express itself like it does on the top picture. Now, the one on the bottom, that's the one you want to find because that's what they show in the books, right? It's like, oh, I found one. Most of those in our region are no longer there because they've been plowed up. And so you don't see the relic, sort of this columnar structure that you search for on field trips. I can point you to some if you want some, but I'm sure that Canada has plenty of those. They don't need to come to the States for those. Okay, so if you look at the soil test, so this is just a screenshot from AgVice working with John Lee back in the day. And so I've highlighted it in the red box there. You can see the soluble salts level in millimoles per centimeter. Millimole per centimeter, decisiemens per meter, they're the same thing. But an EC of 4, okay? Likely, and so another thing about salinity and understanding the values, understand when you send it to a lab, how they're determining salinity, okay? It can be a 1-to-1, like 1 part soil, 1 part water. It can be a 2-to-1, or 2 parts water, 1 part soil, 5-to-1, 1-to-5, whatever you want to say. It's common in Australia to see 1-to-5. We tend to use 1-to-1 because that's what our soil testing labs use, because it's very efficient. Okay. The saturated paste extract is sort of the book standard of what salt levels are in soil. So I ask you, when you look at your values, to understand what lab you send it to and how they're actually determining that, because that really changes then your management if it's a 1-to-5 or a 1-to-2 or a 1-to-1, or if it's saturated paste. Okay, so that's a good example of a saline soil having a fair bit of soluble salts. And so here's one that's you might see, it's like, this is what you want. The other one might be what you have, right? And so this being really low, 0.33, most crops, you will not see any detrimental plant growth or yield reduction in that. So, and we're not going to talk about the solanets, the sodium, the effects of that today. We're just going to focus on just soluble salts in a general sense. Okay, so one of the things that I like to think about this from a pragmatic standpoint, as opposed to sort of like getting down into the weeds. So basically, which salts will likely move faster? So I pose to you, what salts would move faster? Okay, what salts will move faster? Not just the ions themselves. Yeah, the one that is what? Dissolved, right? I mean, it's the one that's got the highest, has the most propensity to go into solution. And so the solubility of the salts is a huge driver, obviously, in whether or not it's going to be in solution and move or not. The other one is flow, saturated versus unsaturated flow. And we'll talk about that. Okay, so this is just some common salts. I guarantee you in the province, it doesn't change between here and North Dakota. These are some common salts that we would have in the soil. And so, calcium carbonate, we talk about lime all the time, right? And we talk about gypsum. We don't necessarily say, oh, what's your Epsom salt concentration, sir? It's like, well, it's pretty high. And say, well, but it helps my feet. But anyway, so then we don't normally see a lot of chloride salts in our region. We tend to see a lot more sulfate-based salts and carbonate-based salts. And so those of you that work, I'm saying this because it's me, those of you that work in the oil and gas industry, sodium chloride tends to be very dominant salt in produced water. And so as the oil comes up, it comes at an emulsion, you need to separate it. The water part is very high in sodium chloride. And so when we look at spill sites for brine, we use chloride as the indicator because of the fact that it's not normally seen in our Western Dakota surface soils. Okay, so let's just compare these three for now. So we know we have calcium carbonate in our soils. We know we have calcium sulfate. We don't have really calcium chloride, but look at the solubility difference of those. Calcium carbonate, if you take a penny, you can even use a Canadian penny, right? You got the queen on one side and you got the whole penny. Down in the States, we have pennies yet because we haven't figured out that it's a worthless piece of currency. And so anyway, if you take a penny and you take off Lincoln's face, right, that's probably how much of that will dissolve in a liter of water. And somebody's got a liter bottle of water, a liter, that's how much will dissolve in there. So how much do you think that will affect plant growth? Probably not at all, right? I mean, let's be honest. So now you take gypsum, calcium sulfate, has a solubility of about 2, let's just say. That's the size, about the mass of a penny. That's in a liter of water. Okay, how much do you think that'll cause problems? Probably not very much, right? It's a fairly insoluble salt. Now, if you had calcium chloride, that's like this much in a liter of water. You think that's going to impact? Likely, right? I mean, so we got to think about how solubility is a big driver in how these things occur. Now, we tend to see a lot of these these salts are what really controls salinity in our region. Calcium sulfate, not so much, but it's dominant. Magnesium sulfate and sodium sulfate. Most of the soils that are saline in North Dakota, we would consider them to be both saline and solanette, just together, right? Because there's just a high concentration of sodium that's also present. And so notice the solubility of those, you know, a little bit, and then you get to more to the kind of the handful kind of size on things. And that's that picture I showed with the top one. Most all of that was magnesium sulfate, sodium sulfate salt. That was being expressed on the surface. Okay, so let's go back on this a little bit. The EC of saturated solution. So if we take that lime, that calcium carbonate, and put it in a liter of water, and you stick an electrical conductivity probe in there, that's the EC you'll get. 0.0, something like that. It's exceptionally low, right? Not even worry about it. If you stick the gypsum, after you put a saturated solution of gypsum, you can pour as much as you want in a liter of water. The EC will not be greater than 2.2. Okay. Do you know what else has an EC of 2.2? Gatorade. Okay. Just as a point of reference. Now, if you do that with calcium chloride, and we just did this the other day, our meter pegs out at about 220. So that's about as high as we can go. And so if you had a saturated solution of calcium chloride, you will not likely get much to grow in that unless it's a halophyte. And so in general, though, if you just think about it, oh, wonder which one's more soluble. Generally chlorides tends to be more soluble than sulfate, which tends to be more soluble than the carbonates. And so if we go then back to this, go back to the corner of that, the EC is 4. Okay. What's driving the electrical conductivity, do you think, in that soil? Is it lime? No. Is it gypsum? No. Something exceptionally more soluble than gypsum. It's probably magnesium sulfate and sodium sulfate. Now, it's not at maybe a super high concentration, but from a plant's perspective, it's high enough, right? And so that's what we're trying to ground ourselves in, kind of what we're talking about with soluble salts, the solubilities, and how that all impacts then the overall electrical conductivity. And it is a fairly inexpensive measurement to make. You can buy a really good meter for $100, $120. And so I don't know what that is in Canada dollars, but is it 500 or something like that? $5,000. And so, but you can get a really good meter and do this yourself. This is not, you know, Jody left, so I don't have to, we're from AgVise, I don't have to say anything, but it is a really inexpensive measurement to make yourself. And so don't think that it's super complicated. Okay, so this is why I asked when you read the abstract, everybody read the abstract, right? It's like the syllabus, everybody reads the syllabus until they want to take the exam at a different time. And then they think, oh, I didn't read the syllabus. Okay, well, that's fine. Anyway, right? Yeah. Anyway, if you would have watched the video, water moves in soil with 2 different forces, gravitational forces and capillary forces. Okay. Gravitational forces is if we take this water, we dump it, the effects of gravity pulls it down, right? That's what pulls it through the actual soil profile. If we look at it from capillary forces, I'm glad we had lunch with a thing that we had a cup with. Somebody can bring this back if they want. Anyway, so the capillary forces, if we think about this, if we notice that the water moves wicks up into it, that's the effect of capillary forces. Okay, capillary forces don't care what direction, right? They just pull. It's pulling, it's suction, if you want to call it that. And so This is what's the unsaturated flow part. And most of our salts when the soil is not saturated are moving this direction. It will only move though if in fact it's soluble in that water, right? If you have a lime, there's no way in the world a lot of lime is going to move up that profile like that, right? If this was all calcium chloride, yeah, it would move up probably quite a bit, and it would then settle above, and as it dried out, it would crystallize. And that's how the salts move up and down in the soil profile. That's soil genesis to the T. If you think of everything as a solubility, if we think of our world as a solubility, that's how we have things where they are, because they've dissolved, they've moved, and so on and so forth. And so it's a good way to think about it. Or at least I tell myself that. Anyway, so let's look at this from a water droplet standpoint. So we're kind of getting to understand how to manage salinity. You have to understand how water moves in soil, period. Okay, period. And that's why I asked you to watch that video, because it helps one to conceptualize how water does kind of move into the soil system. Anyway, so we have the dot on the one side is the gravitational water. And that's like if you take a sponge and you squish out the air and you hold it up and you put it underwater and you hold it up, and it drips out. That's the gravitational water. As soon as that last drop stops, then you're at field capacity. Okay, that's what that sponge is going to hold. That's what that sponge is going to hold. And so tile drainage, right? Tile drainage doesn't, pull water out through a vacuum. There's conceptually people think that. But anyway, but it is the gravitational water that the tile drainage is taking out. And so as you dry down, you get to what's called wilting point. And that's where the theoretical bottom line of where the water will actually be available to plants. Now, in that, between the air dry and the field capacity, that's that capillary water that's moving. Okay, it's not at saturation, it's not gravitational flow, it's the matrix potential that's pulling that water around. That's what's pulling the salts up into the root zone from down below, from the parent material. And that's a fairly common thing that we see. So this is not unlike what happens with salts though, okay? As you have these salts dissolved, you have ions. These ions are hydrated in the soil. They're not just sitting there as an ion, they actually have a sphere of water around them. So for example, if we asked Marla to have a cup of water, and we asked, it starts over here at 100 grams of water, and we let everybody put their finger in it, and then we have Brian drink it, he would not have 100 grams of water to drink, because as you stick your finger in, there's water hydrated around your finger. And so we started with 100 units, but as we got more and more ions, fingers into the pot, he ends up with 25 or 50 units. Okay, so conceptually, that's how water is not available to plants, is because the ions are surrounded by water. And so that's not available for Brian to drink, as an example. Okay, you just want to, yeah, anyway, sorry, Brian. Yeah. That's right. And so going back to sort of like making sure that, we're all on the same page. We have saturated soils, we get rain, we get infiltration, and then we get this drainage effect. That's the gravitational water. It ends up at field capacity, and then you get evaporation and blah, 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 plant uptake, and then you get to the point of wilting point. Okay. And I can't remember where I pulled this from, so I apologize to the author of whoever it was. And so as we think about how water moves into these systems, texture has a huge difference, right? Huge difference. And so the amount of clay really dictates the speed, how fast that water runs. If you have a high clay soil, let's say a long plain series, right? I'm trying to do my due diligence, Megan, here, versus an Osborne. If you have a 2-inch rain on either one of those, which one is going to pond water? It's probably the clay, right? Unless there's other physical limitations. And so as you think about how water is moving through that soil, if your effective rain is only 1/4 of an inch on that clay, but it's 2 inches on the sand, that's a big difference of how much water is going to move down and dissolve that salt and pull it. Okay, so it's not just rainfall, because you have different slopes, you have all this and that. It's the effective rainfall that actually gets into the soil. Okay, so you can't just say, oh, we got a 2-inch rain that went through the tile. No, if gravity is pulling that water off through overland flow faster than it's going in, you're not getting that into the profile. And that's why soil health, the concept of soil health is so important, because if you can take in a 2-inch rain, no matter what the texture, holy moly, you got yourself a really good situation. If you have a soil that is going to shed water right away, you got some issues, because you're going to have a droughty conditions coming in July. In Brian's case, about May or June, somewhere in there. So anyway, so we did some stuff, and I wasn't going to go into this much, but we looked at different clay mineralogies. So kaolinite, we have pockets in North Dakota that are just kaolinite and illite, and we have a lot that's smectite, which we have a lot in the Red River Valley. If we have, this is an example of smectite. I put percent clay on the bottom. This is a saturated hydraulic conductivity, meaning that how fast water is moving through in a saturated system. Okay. It doesn't take much clay to actually restrict water movement, does it? So if you have a clay pan, this is what's happening, right? You just can't get past that. If the water keeps trying to come in, it's going to go overland flow first. But if you have a soil that has a lot of illite or kaolinite, if I would show if I would have shown what I should have done, that number would have stayed almost like 40, no matter what the clay content was. Okay. Why? Because it's a 1-to-1 non-swelling clay. Okay. Versus this one is a 1-to-1 or 2-to-1 swelling clay. And so you have these issues with just the clay mineralogy driving water movement too, which has everything to do with how salts are going to be moved in and out of the soil. So thinking about the capillary rise, unsaturated flow, coarse textured soil, this is all dictated by basically the radius of the pores. In a coarse textured soil, the water might come up 20 inches. 20 inches is all you might get. If you move it to kind of a medium texture soil, 31 inches. You go to a fine texture, 4 feet. We were in Puerto Rico. We were on a soil that was, it was fine clay. And we all sort of like, if the water isn't moving 20 to 30 feet through capillary rise, and it might take years to do it, we'd be surprised, because the porosity just had to be so small, and it was all clay. And so that dictates then how water is going to move through those soils also, but also if you have a groundwater and how high that groundwater is going to move up. If that groundwater is moving up 4 feet, I guarantee you it's probably bringing salts up 4 feet from where it's at. And that's why, when you think about tile drainage, that's why it's also used for that as well. So, if we think about this in a clay soil versus a sand soil at time A, water moves up really slow in a clay. In sand, you can do it yourself. You move it up in sand, it goes whoop, right away, right? It doesn't take hardly any time at all. But if you wait a while, that clay will go way past that sand. Okay, so it's unfortunately in our life, in our time life, water tends to be the thing that we think of, and this is pulling from Les Henry, that water tends to be the soil forming factor of the most significance. Okay, so how do we kind of put all this stuff together? And so we have a conceptual sort of diagram. CRP is our conservation reserve program, or you can say that it's left in grass or something like that. Okay, and so we have a CRP or a grass strip or a road ditch, and so we know that water tends to pond in road ditches sometimes, right? Is that a good thing or a bad thing? Well, it's off the field, so that's a good thing. But how does that actually then impact salt movement? Okay, so then we have a non-perennial plants, cultivated bare soil, warm most of the time because it's been cultivated, not very little residue. And so if we think about this from what's happening, high evaporation, right? There's going to be, if it's warm, really warm, it's going to have a high high evaporation. Compared to the, yeah, you might have high transpiration in the grass, but you have probably pretty low evaporation. Doing what it's supposed to, building soil health. You have really good infiltration of water, right? Good infiltration of water because you have good soil structure. Out in the other location, you probably have low infiltration. So you have a lot less water in the bare field than you would underneath that grass strip or over in that area where the road ditch is. Okay. So now if we start thinking, oh, these salts in this grass strip, we're trying to reclaim this area, let's say. We're going to start moving those salts down. Okay. Which salt is going to move the furthest? Calcium carbonate, gypsum, or something more soluble? Boom, right? Something more soluble. And so you'll see this gradient of salts, okay, over time, not one day, not a week by any means. And so where do they go, right? Where do they go? It's like, oh, now this leaching is greater than evaporation. That's exactly what soil health is supposed to do, right? You're supposed to get water down into the profile. However, on the other side of the equation, evaporation is greater than leaching. So where does the water want to go? High potential to low potential. And what does it bring with it based on what we've shown? You can even see it here. You know, took most of my whiskey right out of there. Took most of it out of there. Where does that water want to go? It wants to move to the area of low potential. What's it going to take with it? Salts, right? In sort of a backwards mentality, that's why you get this, what's called road ditch salinity. And if we have it, you have it, we all have it. And so it's we did this over by Grand Forks. We had a cooperator, excellent cooperator. He had this part of the field on the left of that square. He had this in Conservation Reserve Program. It's a federal program in the United States to take high-risk soils out of production, and they get paid for that. And so this was in CRP for 20 or 30 years because it was saline. Okay, because it was saline. Okay, well, that's good. You can already see what happened next to it, right? What happened next to it, it looks like crap. Why? The salts moved from underneath the CRP out into the field. Why? The same reason we just talked about. There was a low potential of water, good infiltration over here, water moves up and over, and it takes the salts with it, okay? So this is what's called road ditch salinity or some sort of, I'm sure the NRCS, the Natural Resources Conservation Service, doesn't like it when I talk about it, but this kind of thing does cause salinity to move, okay? Okay, so then we said, oh, let's go out and do some sampling because that's what you want to do. And so then we looked at that CRP, we sampled across it. We crossed basically 400 feet and 700 feet out into the field. And so underneath the CRP, look at the EC levels at 0 to 6 just to start with those, okay? They're pretty good, you know, they're not bad. But if you look out over into the cultivated field, the ECs tend to really jump up. Why? Because that salt was moving basically from one spot to the next spot. And so this is a big problem that we have, unfortunately. And so we can, it's a little more hard to alleviate, but in fact, it's, we get questions all the time. What are we supposed to do? And it's like, oh, you know, didn't go out far enough with the actual CRP probably. And so, okay, so that's, okay. Once the salts leach by themselves, yeah, over time. What happens, what has to happen to leach salts? Okay, we talked about this. Go fishing, right? It's like, it's one of those things where it's going to take some time. So you can't just expect, it's not like applying a herbicide where you're going to get immediate satisfaction in a day or two. A lot of these things take time. Leaching has to be greater than evaporation. You have to move water down through the soil profile. You have to have that groundwater level below the capillary fringe. Depending on the soil texture, depends on what depth you need to move that water down. And that's why tile drainage tends to be engineering designed and not designed, you know, on the back of an envelope or a bar napkin or something like that, right? So, okay, so driving that issue in our region, So this is Cavalier, North Dakota. It's not far from Pembina, which a lot of you have crossed at one point in time in your life. Are they still selling ladders on the one side? I can't remember, but we had a change in administration, so I'm not sure if they still sell those or not. Anyway, so this is based on years. This is inches. This is potential evapotranspiration and also precipitation. Okay, what's the stark difference in that? I tell you what, man, getting that as soon as it stops raining and the sun comes out, that water's going up, right? Because that air is dry. And so this ends up being one of our biggest challenges is that we don't oftentimes get a lot of gravitational water to move through. Yeah, we do in the spring oftentimes, but it's also frozen. So we don't necessarily get a lot of water to move down through. And so if we go out to the western part of North Dakota or probably the province, you'll see something very similar. PETs, we measured some PETs in southwest Kansas, like 63 inches. That's why it's irrigated, right? That's why it's irrigated, because you cannot grow corn with that kind of gradient. So, okay, so having a cover helps. So this is just a little snippet of soil temperature taken in late October, but you can notice that at the 3 centimeter depth, you can, with a cover crop, look at the change in the soil temperature. What drives evaporation? Let's start with that. You have to have a gradient, right? You have to have a gradient of vapor pressure, and you have to have some temperature, right? You get sublimation of snow and ice, but it's really, you need the temperature to change the vapor pressure so the water can move from a high concentration to low concentration. If you keep the soil cool, you will decrease evaporation. That's not a great thing in the spring when you're trying to plant, but later in the year, best case scenario, if we could make the soil black, warm it up, and then cover it really quickly after things kind of got settled down, and then store that water for the rest of the season, that would be awesome, right? That's an engineering problem probably in some way, shape, or form, but we could still things to work out. Okay, so for salinity management, drainage. So flushing the soil water and dissolved salts from the soil profile. That's basically having excess gravitational water to move those salts down. Okay, if you can move them down, you can likely allow them to go into a tile drain, and then unfortunately we send them north. So you guys get that, but we're conscious of that. Don't, or I am. Anyway, so then this is drainage is commonly used where groundwater tends to be close to the surface. We have a lot of tile drainage in North Dakota right now, and I'm sure in the valley as well. Up here, they're spaced for gravitational water, right? They're all spaced, but in actuality, I think it should be spaced for actually groundwater control as opposed to gravitational water control. And so, but to get that sort of like that wicking potential down about 4 feet. And then of course the cost can be variable depending on, there's a lot of farmers now that own their own plows. They buy the software, they do it themselves. So it's the price has gone down. And so conceptually, you have tile drainage moves down, right? It goes into the tile, which is slotted, and then it goes to a lower part on the landscape. Or in our part of the country, it goes into a sump, gets pumped out, and then goes into your neighbor's backyard. Okay, so I want to kind of point this out. This is, in soil science, you like to have some history about some things, right? It's like, oh, you remember when, and so I was digging through these and I'm like, I couldn't believe it. I couldn't believe my luck, right? And so I don't know what date, how old this is, John, but anyway, but that's how it used to be done, right? Nobody does that anymore because of they've changed their jobs a little bit, but that's and so modern technology has certainly changed the ability of tile drain to be installed. And so got this data from John Brecker from Agvice. Fortunately, oftentimes they can do this stuff for a long period of time because they have access to land and things for long periods. That's why a lot of master's students have a 2-year project. A lot of field work is 2-year project, right? Because that's how much time a master's student has. And so fortunately with Agvice, they've been exceptional partners with us for a long time and also with many of you, but it does work. right? It does work. You have to, but it takes time. And so it's not an immediate fix. So you have to think about that water moving down, taking the salts with it, taking the ions with it, and then moving them offsite. Okay. Sources of water to leach soils. I think, we live in an area with a lot of blizzards, it seems like. And that's a lot of water. That's a lot of water potential that we can actually trap. And so Harold Stepoon, who was a scientist with Ag Canada out of Swift Current, he's an ag engineer, he's retired, but he was hired for snow management. And so that was at least that's how I remember the story. He was hired for snow management. And he actually has a chapter in a book called snow management. So it's a fascinating read if you're ignorant. So what you need though is rainfall in a sense too, that is slow and steady. You get a turd floater of 5 inches in an hour, you're not moving anything except soil off the soil surface. Melting snow. This is where I think that we actually have our best case scenario of getting water and moving it. Okay. If you think about how much snow is behind a snow fence or a shelter belt, there's a lot of snow that's trapped dense. And so that's water that we can use to actually move that down the profile. Okay, so crop selection. The first thing, go back to that guy, he said, learn to live with it. How are you going to live with it? The first thing you can do is plant crops or varieties that are salt tolerant. This is the first step. Acknowledging you have a problem, right? And then trying to do something about it. The planting side is the most immediate thing you can do. And you can see that barley is, from a production ag standpoint, definitely one of our most salt tolerant crops, where dry beans tend to be a little bit on the weak side. Okay, not all salts are created equal, right? Different solubilities. I want to go back to the sulfur thing though a minute. I was in Puerto Rico after Hurricane Maria, and David Sotomayor, who's a faculty member at the University of Puerto Rico, Mike Wes, they had put sulfur pellets down. And even after Hurricane Maria, which they got like 25 inches of rain, we could see the sulfur pellets on the surface. And so that's a problem with pelletized sulfur, right? We ended up, did a study in Langdon looking at flue gas desulfurization gypsum, calcium sulfate, and our yields were the same no matter what we use, but that stuff is like $5 a ton. And so different types of products, calcium sulfate can be used for that purpose if you have access to it. So there is other uses as well. If you can understand how water moves in soil, you can begin to understand how to manage salinity. This is like I preach this in my class. You have to understand how water moves before you can manage the salts. If you can't stop the problem, you're not ever going to fix it. You have to understand where the problem is starting from. Crop and variety selection may help maximize profits. This is my hope, but and then taking saline, this is not a popular one. We have a problem in North Dakota. We have livestock, we just don't have enough of it. If we had a way to manage some of these problem soils with livestock, we'd be much better off. But we force them to be corn and soybean and wheat, or dry beans or something else. And so that's not a great way of actually managing the soils long-term, in my opinion. And so the tile drainage must be installed with the correct spacing and with that in mind. Okay, so we do have our public, I'm gonna forget the name. Yeah. Public radio. Anyway, so there's a video called Salt of the Earth, and one can watch it. It highlights some work that was done in Manitoba as well, but it's a really good story about managing salts. One of my former student, Lee Breeze, he's in there quite a bit from the crop advisor side of things. And so if you find time to watch it, you should be able to run the Google machine and find it on there. On the abstract again, that video, how water moves in soil, please watch that if you haven't already. And then I'll take any questions that might come up. Thank you.
I was agonizing whether we're going to take any questions at all, but Marla has one.
I have one question from the online. that I wanted to pose to you, Tom. There's a promotion of humic acid additions to help crops grow in saline areas. Is there any truth to this?
Can you repeat the question? The first part, I didn't quite catch.
The promotion of humic acids
Oh,
in order to promote crop growth in saline areas.
I would say that the first thing you do is you manage the crop that is there. Do I have my own research to say things work or don't work? No. But conceptually, salts have to be managed with the water and not with products. The concentration of salts in the soil is exceptionally high when you have saline soils. And to think about one thing, whether it's nanoparticles or something else, that's going to be a very difficult sell to me because of the fact that you'd have to apply tons of it per acre as opposed to ounces or something like that. So now I will say that there are movements ahead. Glick, he was out of Canada. They looked at plant growth promoting bacteria. And what it does is it actually tricks the plant to not produce ethylene. And so when a plant produces ethylene, then it says, oh, I'm hurt. But if you can trick it not to produce ethylene, then they'll actually grow in more harsh conditions. And so Elizabeth Murray with Earthmaster out of Calgary, they do a lot of reclamation work. They bought the patent for that process, and they use it in their brine impacted soils. They've had some decent success with stuff like that. And so, but no, I haven't learned anything about humic acids being a key in managing salinity.